Hello everyone, and welcome back to the videos on the fundamentals of math. In this video I will be talking about multiplication and division of rational numbers. This is a technical skills video. And I think we'll begin with multiplication. Now when we talk about the algorithm for multiplying rational numbers, this algorithm is sort of based on four key structures that I would like to talk about before I give you the algorithm itself. So the algorithm basically combines these four key structures in any order. One is 2 times 3/5. In such a case, if you think about what the problem is trying to do, we have 3 pieces, each one is a fifth, and we want to double the amount. And in order to do that, what we can do is we can multiply the number of pieces by 2. So instead of 3 pieces, each of which is a fifth, we'll take 6 of them. And this explains why we can multiply 2, which incidentally you can think of as 2 over 1. So it's in the numerator. That explains why we can multiply numerators. And so here we can multiply 2 by 3 to double the number of pieces that we are taking. And so we'll end up with 6/5. The second key structure is similar to the one above. Again, we have 3 pieces. This time each one is an eighth, and we want to double the number of pieces, or we want to double the amount, the total amount that we have. And of course we could do what we did with 2 times 3/5. We could say that if we have 3 pieces, each of which is an eighth, we can double the number of pieces and end up with 6 of those. The only problem is in this case we'll end up with 6/8, and then we will have to reduce the fraction. And although with numbers like 6 and 8 this may not be an issue, you'll find that quite often these numbers tend to grow very, very quickly, especially when you have multiple fractions that you're dealing with. In such a case, if it's possible to do a reduction 2 and 8, we can divide both of them by 2. Then this move is allowed. And in fact, it's interesting what it is that this kind of a move achieves. If you think about what we have here is 3 pieces, each one is an eighth. Now, if you think of an eighth and compare that to the size of a quarter, if you think of let's say pizza, and you cut it into 8 parts, so like a plus and then a times symbol, and imagine the size of 1 piece, and then imagine cutting a pie into 4 parts and imagine the size of 1 piece. A quarter is twice bigger than an eighth. And when we reduce, we basically change the size of a piece. Instead of an eighth, when we divide 8 by 2 and we get 4, instead of an eighth, now we are talking about quarters, and each piece is twice bigger. And so 3/4 would be 3 pieces, each of which is a quarter. 3/8 is 3 pieces, each one is an eighth, and 3/4 then is twice bigger than 3/8. So we reduce, and we get 3/4. So again, one more time, what happened here is that when we reduced, we doubled the size of a piece, and but we kept the number of pieces the same. So we are still taking 3 pieces, but each piece here is twice bigger than each piece here with an eighth. The third key structure is one similar to the problem 1/2 times 3/5, which is, in a sense, it tries to find half of 3/5. And for this problem, what we can do is we can multiply 2 and 5. When we multiply 2 and 5, of course, we'll end up with 10. We get 3/10. And if you compare what's happening here, is that going from 5 to 10, we have divided the size of a piece by 2. So each piece becomes half as large. And we are still taking 3 pieces, but in 3/10, each piece is half as large as 1 in 3/5. And that way we achieve half of 3/5 by dividing the size of each piece in half. And that also explains why we can multiply denominators when we multiply fractions. The fourth key structure is when we have 1/2 times 4/5. And in this case, we can simplify 2 and 4. And again, what we are doing here is that the argument is if we want to find half of 4/5, then we divide the number of pieces by 2. And so instead of 4/5, now we have 2/5, which is pretty much half of 4/5. So these are the 4 key structures. The second one and the fourth one are the ones where you can do reduction. You can reduce 2 and 8, and here you can reduce 2 and 4. And these two together go with step 1 in the algorithm. The algorithm, step 1 is reduce any numerator with any denominator and keep doing that over and over. So that would be, for example, 2 and 8. 2 is in the numerator because you can think of it as 2 over 1, and 8 is in the denominator. We can reduce those, or we can reduce 2 and 4 here. 2 is is a denominator and 4 is a numerator. You can never ever, of course, reduce 2 numerators or 2 denominators. It has to be always 1 numerator, 1 denominator, because that's the way the logic here and here works. And once you've done your reductions, that would be taking these 2 steps over and over until nothing more can be reduced. Then we follow steps 1 and 3, which says you can multiply the top numbers, so double the number of pieces in this case, or multiply the bottom numbers, which divides the number of a piece by 2. Okay, so the algorithm is reduce any numerator with any denominator, and then keep doing that until you cannot do this anymore. And then multiply the numerators and multiply the denominators. Now let's take a look at some examples. Problem number 1, 4/5 times 1 over 6. And here what we can do is we can reduce 4 and 6. 2 goes into both 4 and 6. So we divide 4 by 2, and then we divide 6 by 2. And now that's step number 1, reduce any numerator with any denominator. And I cannot reduce anything more. 2 and 5 have nothing in common, and 2 and 3 have nothing in common. So we multiply the numerators and we get 2, and we multiply the denominators and we get 15. Problem number 2, 8 over 35 times 14 over 6. Now in some cases, like in this problem, we may be able to reduce more than once, of course. So that's where the repeat as many times as you can comes in. So if I show you the reduction for this product, we have 8 over 35 times 14 over 6. Now we do have options here. We can start with 8 and 6, and we can divide both by 2. 2 goes into both 8 and 6. We could also start with 14 and 6. 2 goes into both of those as well. So the numerator and the denominator could belong to the same fraction, of course. We could also do 35 and 14. 7 goes into both. So we do have options, and it's quite interesting that it doesn't matter in what order you do the reductions. Whether you start with 8 and 6 or start with 14 and 6, you will always end up with the same final answer. And you should actually try that a couple of times just to see it for yourself, that you do always get the same result in the end. So here we start with 8 and 6, and we reduce 8 and 6, divide by 2 to get 4, and then divide 6 by 2 to get 3. And then we reduce 35 and 14. 7 goes into both. 35 divided by 7 is 5, and 14 divided by 7 is 2. Now this step where it says reduce any numerator with any denominator is done. 4 and 5 have nothing in common, neither do 4 and 3. Same for 2, 5, and 2 and 3, so nothing more can be reduced. Keep in mind, you may not reduce 4 and 2. They're both in the numerator. It has to be one from top, one from bottom, based on the logic that we talked about here with the 4 key cases up here. Okay, so now that all the reductions are done, we multiply, we go to step number 2, multiply numerators. So 4 times 2, 8, and then multiply denominators. We get 8 15ths. Problem number 3. Now sometimes you have, of course, negative numbers. In such a case, I strongly advise you to work out the negative sign. Don't get stuck with all these negatives, especially when the expressions become longer. you can simplify all of your negatives following the same rule that we had for integers. So here we have an odd number of negatives. There are 3 of them, and so the answer will be negative. So we write down equals and we record the negative sign. Now that we have dealt with the sign, we don't have to worry about it anymore. So you can ignore all of these signs now, and therefore the focus is on 1, 2, 4, and 5. 2 and 4 can be reduced using 2. And nothing more can be reduced. So we multiply 1 by 2. You see, I'm totally ignoring the signs now. We multiply 1 by 2, and then we multiply 1 by 5. And we end up with 2/5. So the answer is negative 2/5. Now, in case you have mixed numbers and natural numbers present, then what you should do, of course, is change these into improper fractions. It is very, very time consuming. Occasionally that may not be the case, but usually it's very, very time consuming to multiply, let's say, 2 mixed numbers together, and if you have more of them, it's even worse. It's usually much faster if you convert to improper fractions. So in this case, we get 3 times 3, 9, plus 1, 10. And 2 becomes 2/1. Now how you go about making these moves is something I've discussed in the video on the structure of rational numbers. And so that this video doesn't become too long, I'm not going to repeat that. Please take a look at that video, and then you'll find out, you'll know how to go from 3 1/3 to 10/3. But the short of it is, we multiply 3 by 3 to get 9, and then add 1 to get 10. So we get 10/3, and natural numbers go over 1. 2 is the same as 2 1s. Now that we have converted them into improper fractions, now we reduce. Please make sure that you remember what I say now. Do not reduce until you have converted them to improper fractions, because the majority of times it will not work. Okay, so we can reduce 10 and 5, and as you can see, I can again, the numerators and denominators don't have to belong to fractions that are next to each other. There can be other fractions in between, so long as you have chain multiplication, nothing else. You can now reduce 10 and 5. 5 goes into both, and now nothing else reduces. So we multiply the top numbers, which is 2 times 2 times 1, that gives us 4. And then multiplying the denominators will give me 3. And so we have 4/3. Now keep in mind that it's a nice thing to do if you have an improper fraction as your final answer. Change it to a mixed number so that your readers know how much you're talking about at a glance. Now again, how you go from an improper fraction to a mixed number, and also up here how to go from a mixed number to an improper fraction, is something that you can find more information about in the video on the structure of rational numbers. Okay, so a couple of things that you should avoid, and this is important. Number one is it's very common for people to, as soon as they see a multiplication of fractions, to go ahead and multiply the numerators and then multiply the denominators and then start reducing. Keep in mind that such a thing can result in values that are very, very large. So for example, if I try to do 13/21 times 35/26, if your times table is good, you can actually do this in your head. See 13 and 26, you can reduce using 13. You get 1 here and 2 here. So remember that, 1, 2. 21 and 35, 7 goes in 3 times and 5 times. So we have 1, 2, 3, 5. And now we have 1 times 5, 5, and 3 times 2, 6. And the answer is 5/6. You can pick up a piece of paper and do the reduction on paper if you like. Reduce 13 and 26, you get 1 and 2, and then reduce 21 and 35, you get, using 7, you get 3 and 5. And then 1 times 5, 5, 3 times 2, 6, and we get 5/6. So it's not that difficult to do with these numbers, but if I switch the order of the algorithm and do the multiplication of the top numbers and multiply the bottom numbers, then this can result in large values. Now I have 455/546. And you know what's quite interesting is that you know the 13 that we used to reduce 13 and 26 here, that same 13 can now be used to reduce 455 and 546. But I don't see that anymore. You see, it's so easy to see that 13 goes into 13 and 26 here, but it's totally hidden now. And the same thing is true for 7. I can so easily see that 7 goes into 21 3 times and into 35 5 times, but I don't see that here anymore. And if I use 13 here, then guaranteed you will have to use 13 here as well when you reduce. And same thing for 7. So make sure that you reduce first and then multiply the numerators and denominators. Look, you're going to have to do the reduction at some point. Do it when the numbers are small. The second thing not to do is use BEDMAS. And here's the problem, one small problem that can, well, it's not a small problem, one problem out of the many issues that can come up with the use of BEDMAS. Let's say that we are doing this multiplication now, where I put the fraction 8/9 in between those two. So now we have 13 over 21 times 8 over 9 times 35 over 26. Now again, we can reduce 13 and 26. We can reduce 21 and 35 using 7. And but if I use BEDMAS, BEDMAS says that I have to go from left to right and taking care of the first multiplication that I see. And by limiting me to this product here, I lose my chance to reduce 13 and 26 before the numbers become large. Now, if I multiply 13 by 8 to get 104 and 21 by 9 to get 189, nothing reduces here, by the way. I get 104 over 189. Now 13 goes into both 26 and 104. I know that because 104 comes from 13 times 8, but I don't see that anymore. And same thing for 7, which went into 21 and 35. It goes into 189 and 35. I see that in 35, but I don't see it in 189 anymore. And so that's one of the drawbacks of BEDMAS, by limiting you to take a look at, by limiting you to go from left to right. Not only does it give you the wrong impression that that's the only way that an expression can be evaluated, but also it can result in intermediate values that are sort of unpleasant to work with. Okay, let's now move on to the next topic, which is division of rationals. And basically the final thing that we want to come to is that if you're dividing by a fraction such as a over b, you can switch to multiplication by its reciprocal. The reciprocal of a over b is b over a. So you basically flip the fraction. So division becomes multiplication, and the fraction that follows division becomes its reciprocal. Now to explain how is it that this is true, take a look at the diagram on the right side. On the top, let's say going to the right, with the arrow pointing to the right, we are multiplying by m over n. And of course, division by m over n should do the opposite of multiplication by m over n. Now, we can view multiplication by m over n as multiplication by the top and division by the bottom, times the top and divide by the bottom. And if I want to go back, then I have to multiply by n and divide by m. And so the sequence becomes multiply by n and divide by m. Multiply by n places n on the top. Divide by m places m down. And so we can see that division by m over n is the same as multiplication by n over m. Okay, as an example of how we work out division problems, let's take a look at the problem 2/5 divide by -3 over 10. Now here division by -3 over 10 becomes multiplication by 10 over -3. Now before you do that, by the way, once again, I recommend that you work out the sign first. And the reason is, now in this case there is only one negative sign, and that may not be that big of an issue. But still getting into that habit is a good one. So overall we have one negative, and we get a negative sign, we write it down, and then from now on we can ignore the negative sign. Now we have 2/5, and then we multiply by the reciprocal, which is 10/3. Okay, now we can reduce 5 and 10. 5 goes in once, 5 goes in twice. Nothing else reduces. So we multiply the top numbers and we multiply the bottom numbers to get negative 4/3. Convert to a mixed number to get negative 1 and 1/3. And the last topic for this video is on complex fractions. Now, complex fractions are fractions where you have where the top or the bottom itself has fractions. And as an example of this, we have the complex fraction 2/3 divided by 5/7. It's important that you pay attention to the longest line, and when you write your own complex fractions, make sure that it's quite clear what the longest line is, because that becomes the main division. So in this case, we interpret what you see as 2/3 divided by 5/7. So the numerator has 2/3 in it and denominator has 5/7. Now if you make this line longer, then only 2 is in the top and everything else is in the denominator. And the same thing if you make this one longer, things change. And by the way, not all of these are the same. Some of them may turn out to be the same, some of them are different from the others, and therefore it's always very important to make the longest line, the main division line, visibly longer than other ones, so that it's clear what's on the top and what's there. Now to work out these kinds of problems, this complex fraction, what we do is we notice that what we're talking about again is that we have a over b on the top, and then we are dividing that by c over d. And if I use the double dot notation, by the way, it would look like this. You see division by c over d, and here we have division by c over d. And we know division by c over d becomes multiplication by d over c. So it turns into multiplication by its reciprocal. So basically division by c over d can be turned into multiplication by d over c. Now some people like to put a and d on top, so it becomes a times d divided by b times c. This has the advantage of maintaining the nature of one fraction that we have when we take a look at this. And the mnemonic that's usually used for this kind of division is that if you have a over b divided by c over d, the very top and the very bottom numbers multiply and they go on top, and the middle two multiply and go down. If we go back to the previous diagram, you can see that we ended up with AD on top, that's A and D, and then we ended up with B and C down here, which are the middle two values. So here's the mnemonic again. The top, the very top and the very bottom multiply, go on top, and the middle two go down. Now this is nice because it's a nice shortcut, and it's a good one to know in algebra. Frequently enough, you'll come across this kind of expression, so it's good to know how to quickly simplify it. Okay, now let's take a look at the problem that we are working on. 2/3 divided by 5/7, and so this becomes equal to, we multiply 2 and 7, we place that on top, then we multiply 3 and 5 and we place that down. Nothing reduces, and therefore we get 14 over 15. All right, next we have 4/15 over 2 over 35. And one of the reasons that I wrote this down, 2 times 7 and then 3 times 5, you might wonder, why didn't I just multiply 2 by 7, put down 14, and multiply 3 by 5 and put down 15? In some cases, if you're sure that the final answer cannot be reduced, do that. But if you have any doubts, it's better to write this stage down, this step down, because then you might be able to reduce. And that's the case with problem 7. 4 over 15 divided by 2 over 35. And we multiply 4 and 35, place that on top, and then we multiply 15 and 2 and place that down. Now we can do a fair amount of reduction. Remember that if you don't reduce now, you will have to do that at the end. 4 and 2 we can reduce to 2 and 1. 2 into 4 twice, and 2 into 2 once. 15 and 35 we can reduce to 3 and 7 using 5. So 5 into 15 goes 3 times, and 5 into 35 goes 7 times. Now we multiply the top numbers to get 14, and we multiply the bottom numbers to get 3. and we convert to a mixed number. Two more problems. Problem number 8. On the top we have a natural number, and the denominator is 3.5, which is a mixed number. So here we have to convert them to improper fractions. On the top we get 8/1, and denominator becomes 3 times 2, 6, plus 1, 7/2. Now we take the shortcut. 8 times 2 goes on top, and 1 times 7 goes down. We end up with 16/7, which is 2 and 2/7. And the final example has some negative values in it. -3/4 divided by -1 over -5. And here again we work out the sign. Overall we have 3 negatives. You see, anytime you have in the absence of anything other than multiplication and division, you can always go by the rule that we had for integers, for multiplying and dividing integers. An even number of negatives means the answer is positive. An odd number of negatives means the answer is negative. In this case I have 3 negatives, and so the answer will be negative. Let's take care of the sign, and then we ignore the sign. Now we multiply 3 and 5, that goes on top, and we multiply 4 and 1, and that goes down, and so we end up with -15/4, which changes into -3 and 3/4. And that brings us to the end of this video. Thank you as always for watching, and I'll see you in the next one, which is on expressions with rational.